Okay, reaction mechanisms. A reaction mechanism, if you want to describe it in the easiest terms possible, is what hits what when. When you're down at the molecular level, when you're looking at individual molecules and individual species in solution, what thing hits what other thing and when does it hit it? That is the reaction mechanism. A more scientific answer to what is a mechanism: it is the real path the reaction takes. It is a sequence of elementary steps. It is a sequence of reactions that, when you add up all these reactions, give you the overall reaction. For example, here's an overall reaction. 2NO gas plus O2 gas goes to 2NO2 gas. But the question is, how does this reaction actually occur? What hits what when? You've got two nitric oxides, you've got an O2. What's going to slam into what? It turns out, when we look at the mechanism, what we find out, what really is going on in this reaction, the first step is two nitric oxides slam into each other and make an N2O2. So that's the first step. Two NOs create N2O2. Then this N2O2 hits an oxygen and converts that into two NO2s. So that's the thing that happens. Two NOs slam together to make N2O2, and then an oxygen hits that N2O2, and the whole thing breaks apart to form two NO2s. That's the two elementary steps here. Note, the first thing that was made is this N2O2, which is not part of this reaction. It's not a reactant, it's not a product. We call that an intermediate. So the two NOs get together to make the N2O2 intermediate, and in the next reaction, the intermediate gets used up by the oxygen to form the product. If you add these two reactions, you remember Hess's law from last semester: anything that appears the same on both sides you can just get rid of. And so when you can get rid of the intermediate, we get our overall reaction here, 2 NOs plus O2 goes to 2 NO2. All right, now, when we're looking at this, we're going to define the molecularity of the reaction, which means in the slowest step, in the step that takes the longest amount of time, how many things are smacking into each other. Now, we're going to discuss this a lot further, but note, in this step right here, the top step, these two NOs, one NO must smack into another NO, so this step is bimolecular. Bimolecular means two molecules reacting. Note this step down here, the intermediate plus the O2, is also a bimolecular step. So both these steps are bimolecular. What we're going to find out, the slow step is the first step, and the slow step is bimolecular the reaction is bimolecular since that slow step is bimolecular. All right, so let's look at some rules here for our elementary steps and how that corresponds to the rate law. So what we're looking at now is for an elementary step, not the overall reaction, just an elementary step. It turns out, for an elementary step, the rate law can be determined from the stoichiometry of the reaction. For an elementary step, the rate law does come from the reaction of that step. For example, in our reaction down here, here's our overall reaction right here. This is the overall reaction, so we do not know what the rate law is, but we know the form of the rate law. The form of the rate law is rate equals K times the concentration of NO to some power X times the concentration of O2 to some power Y. We know the form of the rate law, but we don't know what this X and Y are. However, when we look at the mechanism, these two steps here are the mechanism, the sequence of elementary steps. This reaction has two elementary steps. The rate law of the elementary steps, X and Y, are the stoichiometry. So for this step right here, the rate law is rate equals K, let's call this K1 since it's the first step, times the concentration of NO squared. For an elementary step, the rate law can be determined from the coefficients, from the stoichiometry. That determines X and Y for an elementary step, not for the overall reaction, just the elementary step. Which means we can figure out the rate law for this elementary step down here. Rate equals, let's call it K2 since it's the second step, times the concentration of N2O2 to the first power times the concentration of O2 to the first power. Again, with elementary steps, with each little elementary step that when added together, they all make the overall reaction, but with each elementary step, the rate law of the elementary step can be determined from the coefficients, but not the rate law for the overall reaction. Now that's going to be important because as we look through our rules here, we can then use experiments to determine if any reaction that we see is itself a one elementary step reaction or if it's a combination of steps. Because it turns out, very important, the rate law for the overall reaction is going to be the same as the rate law of one of those elementary steps. When you do the experiments, okay, run the reaction, change the concentration of one of the reactants, run it again, change the concentration of the other reactants, run it again. When you get the overall rate law for the overall reaction, it will be the same as the rate law of one of those elementary steps. It'll be the rate law for the slowest elementary step, the rate determining step. Because the speed of the overall reaction literally depends on only the speed of the slowest step. If your reaction has 5 steps, 5 elementary steps, it's the slowest step that determines the speed of the reaction. And you might be saying, but don't the other steps add something to the speed of the reaction too? The answer is not really. And let's look at it this way. Let's look at the elementary steps to drive from campus to Denver, Colorado. All right, step 1, travel from Quivira to 435. That takes about 2 minutes. Step 2, travel on 435 to I-70. That takes maybe 10 minutes. Step 3, drive on I-70 to Denver. Well, that takes about 10 hours or so. Can we see the slowest step, the step that takes the longest, is once we get on 70, getting to Denver. That's 10 hours. And note, that step is 10 hours. The whole trip is like 10 hours and 12 minutes. Therefore, this slowest step here really determines the rate of the reaction. And what we're going to see here is how much quicker will you get to Denver if you travel twice as fast on I-435? Or from Quivira to 435. What if instead of 2 minutes, this only takes 1 minute? How much faster are you getting to Denver? Well, instead of 10 hours and 12 minutes, it takes 10 hours and 11 minutes. We can see that really doesn't cut down the trip time very much at all, percentage-wise. What if you doubled your speed on this part? Now, don't go out and do this. The police might not care for that. But if instead of 10 minutes from 435 to I-70, it only took you 5 minutes, you doubled your speed on this step, still, looking at the overall time, you didn't save yourself that much time percentage-wise. But now, what if you doubled your speed on I-70? Instead of 10 hours, this took only 5 hours. Well, now our whole reaction's only going to take a little over 5 hours. Doubling the speed of the slowest step doubles the rate of the reaction, the reaction time is cut in half by doubling the speed of the slowest step. And realize something, that when we're looking at these steps here, yeah, these two steps are definitely much shorter than this one. But when you're looking at reaction mechanisms, the slow step is like 1,000,000 times slower than the next slowest step. Fast steps go 1,000,000 times faster than slow steps. So when we look at it that way, increasing the speed of a fast step will only increase how fast a reaction occurs by 0.00001%. Whereas increasing the speed of the slow step doubles the speed of the reaction. So it is really just the slow step, the slowest elementary step, that determines the speed of the overall reaction. And because of that, the rate law of the slowest elementary step is the same as the rate law of the overall reaction. Okay, let's look at an example here. So let's look at the decomposition of hydrogen peroxide, which is facilitated by iodide ions. If you take I- and H2O2, H2O2 is hydrogen peroxide, and mix those two together, you'll get water plus O2 plus I- again. Note we put I- in and we get I- back out. Anytime you put in a reactant and at the end of the reaction you still have that reactant left over, it's as if it's not involved. It is, it just doesn't look that way with the overall reaction. We call that a catalyst, something that speeds up a reaction, but you get it back at the end. That's our catalyst. Well, the question is, what is the rate law for this reaction? Well, the first thing we can say, we know the form of the rate law. The form of the rate law is going to be rate equals K times the concentration of H2O2 to some power X times the concentration of I- to some power Y. Okay, then how do we figure out X and Y? We run our experiments. We double the concentration of H2O2, see what that does to the rate, double the concentration of I-, see what that does to the rate, and when we do that from running those experiments, we find that the rate equals K times the concentration of H2O2 to the first power times the concentration of I- to the first power. All right. So, what does that tell us about our mechanism? Well, recall that the rate law for the overall reaction here has to be the exact same as the rate law for the slowest step. So this tells us our slowest step has 1 molecule of H2O2 in it and 1 molecule of I- in it reacting. And that's it. It tells us that H2O2 plus I- must go to something. Now, at this time, we might not know what that something is, but we know H2O2 plus I- has to go to something, has to make some products, because since this is an elementary step, since this step right here is an elementary step, we know the rate law for this very step 1 here is rate equals K, let's call it K1, times the concentration of H2O2 times the concentration of I-. Because for an elementary step, it's the stoichiometry determines X and Y. Note this rate law here is the same as our overall rate law. So we know H2O2 plus I- must go to something, has to be the slow step. Because that step's rate law is the same as our overall rate law. Now the question is, what does it go to? Well, when you're figuring these out, if you're not sure, H2O2 plus I- must go to something, is there any way to make one of the products? And we know, water is a product, so let's just put water in there and see if that works. And then if water goes in there, then maybe the next thing is IO-. I wouldn't expect you at this point to know these, but in the future I'd expect you to, with your knowledge of chemistry, to predict some of the things that might occur here. But note, we only have one H2O2 and one I- making water, one of our products, and we have IO-, which is not a product of this reaction. So we know if we made IO minus in step 1, the next step we probably have to get rid of this intermediate IO minus. And so we know we need IO minus in the next step to get rid of it, since it's an intermediate, it's not a part of this overall reaction. And the question is, what must we react this IO minus with? Well, if we look at our overall reaction, we needed two H2O2s, two hydrogen peroxides. Because when we add up these equations, we must get the overall reaction. So let's throw in that second H2O2. We used one of them here. Let's throw in that second H2O2 to react with the IO minus. And when we do that, can we make more product? Well, we've already made one H2O. We need to make another H2O, an O2, and we've got to get our I minus back again. If we look at our elements here, yes, we can make H2O, O2, and make I minus. And so this is our proposed mechanism here, where the slow step, step 1, is hydrogen peroxide plus iodide goes to water and IO minus. The fast step, step 2, is another hydrogen peroxide reacts with the IO minus intermediate to make water O2 and regenerate our catalyst I minus again. Okay. Now the question is, though, how do we know if this mechanism is the correct mechanism? How do we know if this mechanism is right? And that's not always the easiest to figure out. Actually, a lot of chemistry goes into trying to find out if this is the right mechanism or not. But one way to look for it is this mechanism predicts that we make IO minus. We're predicting IO minus is generated in this reaction. Let's try to see if we can find IO minus in our reaction, see if it even exists in the reaction. That's one way to do it, is like look for the intermediate, see if that intermediate is in there. And in a little bit we'll discuss other ways to see if our proposed mechanism is the actual mechanism. For this reaction, when this was run and first looked at to figure out the mechanism, they did find the presence of IO minus in the reaction, which means, okay, whatever our mechanism is, it must produce an IO minus intermediate, and this mechanism did a really good job of that. So let's look at an example, just a very general example. In truth, on exams, while we might have some specific problems where I want you to figure out the mechanism, I want to know your thinking on how we figure out mechanisms, so there'll be a number of problems that have just a general reaction. So here's our very general reaction here. Let's say we have x2 plus y plus z goes to xy plus xz. Now, since this is x2, this would be something like O2 or maybe N2 plus like sodium plus like oxygen or something like that. N2 plus Na plus O, or something along those lines. These guys represent individual elements, and this represents a diatomic. Okay, and so the question is, and it starts easy, here's our reaction. X2 plus Y plus Z goes to XY plus XZ. What's the mechanism? Well, how do we figure out the mechanism? Well, the first thing we remember is, well, I know if I could figure out my overall rate law, that will be the rate law of the slow step, so that will tell me the reactants in the slow step. So that's the first thing we need to concern ourselves with. What are the reactants in the slow step? Well, how do you find the overall rate law so we get that? Well, you double the concentration of X2, we find that doubles the rate. Recall from previous, if doubling the concentration of X2 doubles the rate, that means it is first order. The rate law is first order in X2. Tripling the concentration of Y triples the rate. 3 to the Y equals 3. So it is first order in Y. Doubling the concentration of Z has no effect on the rate, does not change the rate. So this here, the Z, doubling Z, 2 to the Z power equals 1. Z equals 0. There's no effect on the rate due to reactant Z. So from this information, we can say that the overall rate law is rate equals K times the concentration of X2 times the concentration of Y. Doubling X2 doubles the rate, means it's first order in X2. Doubling y doubles the rate means it's first order in y. Doubling z has no effect on the rate. Z is not in here. So here's the rate law for our overall reaction. Realize this is also the rate law for our slow step, meaning that the slow step is x plus y goes to something. We can just write that down right now. X plus y has to go to something. Well, the question is, what do x and y go to? That we don't know. We have to just come up with some ideas. We have to brainstorm this. But a nice thing to look for is, well, is there any way we can make some product here? That's always a good thing, making product. If I have x2 and y, can I possibly make one of my products? Well, note I can't make xz. There's no z in here, but I can make xy. So what if x2 plus y goes to xy plus x? Let's just propose that. Note, I've made my product xy, that's good, but x, just x by itself, is not a product, therefore it must be an intermediate. So what I want to do now is, since I had generated this intermediate in this step, in the very next step, it's probably a good idea to get rid of that intermediate. So bring our intermediate down, x, and what are we going to react it with? Well, we have not yet put z in our reaction yet, in our mechanism, so let's say x plus z. Well, wouldn't those go to xz, the other product? So this is our proposed mechanism here. x2 plus y goes to xy plus x. X plus z goes to xz. When we do Hess's law and add these two together, x is the intermediate, we get x2 plus y plus z goes to xy plus xz. And that is our proposed reaction. That's our proposed mechanism. How would we know if it's true or not? How would we know if this actually is the right mechanism? We'd have to look to see if we can find intermediate x, whatever that is, when we're running the reaction. See if we can find this intermediate x. That's how we would figure that out. All right, this video got a little long, so let's stop it here, and then let's go in our next video to this example. Here's a reaction. The question is, what's the mechanism for this reaction? We'll do that example next.